So our syllabus says that we have to both be able to select and use data from different analytical techniques to work out the structure of organic molecules, as well as analyze data from spectra. And in this case, it only mentions the mass spectrometry and our infrared spectroscopy to solve problems and communicate our conceptual understanding as well as make predictions. So let's look at an example question that actually involves some of this. So this is the Victorian chemistry exam from 2018. And in this question, I've actually been given a little bit of information as a clue. So I've been told at the beginning that my only elements present are carbon, nitrogen, and hydrogen, and they exist in the ratio of 4:1:11, which means I can actually work out my empirical formula as being C4N-H11. And this will then help us in interpreting both the infrared spectra and the mass spectra that's actually given later in the question. So we've been told that this is the infrared spectra of the chemical, and then we're asked to identify specific wave numbers and the bonds that are associated with them. So for that, we actually have to use our infrared data from our actual formula and data booklet. And if you remember, when we actually have our infrared data table, our wave numbers increase as we go down. So that means that I'm looking for 2956, which would be this peak here, and the 3376, which will be this peak here, because this is 3000, 3500, 4000. So I need to go down my table till I find about, so it's not going to be, so it could be maybe in this range, it's unlikely, and it could be in this range. So I've been given an extra bit of information in the fact that it hasn't got oxygen in, so it can't be a carboxylic acid. So I know straight up that it's going to be the CH. But if I hadn't been given that piece of information, I also know that for a carboxylic acid, that it's a C double bond O to a OH, which means to have that as a carboxylic acid, it would also have to have the carbonyl group, which is about 1700 to 1750. So it means I'd be looking for a peak in this region, which does not exist. So we know it's not a carboxylic acid. So I can have ruled that one out even if I wasn't given that information. So I then would write my answer is that it's a CH bond. My 337 peak over here, again, it could be in either of these. However, again, I'm told that it's not OH, so I know it's the NH, an amine type peak. But I also remember in terms of OH that they're always quite broad peaks. So rather than being really shallow or quite narrow across here, it's a more broadish type peak, so I'd see a larger peak. And so I know it can't be this one. And I remember broad by the fact that when you say O, your mouth goes really wide, so it's a wide or broad peak. So we know it's the NH. Something that actually helps me from the fact that this is a molar tooth shaped peak is that I know that this is a primary amine. And the reason it's actually a primary amine, if we actually think about it, each of these is an NH, each of those little peaks. So if it's a primary amine, it has two NH, and the other bond is a carbon. So it has two of these NHs to actually make those two peaks. Remember, a secondary amine just has a single peak because its nitrogen has one hydrogen, but it's now bound to two carbons to make it that secondary amine. And our tertiary amine doesn't actually get a peak at all because in this case, the nitrogens are bound to three carbons to make it the tertiary amine, so there is no NH, so therefore there would be no peak at this point. So this is actually going to help me later in terms of knowing that little bit of extra information. So the next part of the question then introduces mass spectrometry. So mass spectrometry data is masses of fragments and masses of the parent compound. So remember that our peak that has the biggest mass is our parent peak, and this is this one here. We may sometimes see these little tiny peaks just occurring at the M+1. So we call this the M+ or parent ion. The N+1 is caused because of the extra carbon-14. So 1% of our natural isotopes of carbon are carbon-14. So you may see a very small relative peak in size to the parent peak. So in this case, I remember that my ratio was the C4N H11, because we were told that ratio in the beginning as information. So therefore, I need to work out what's the molecular formula. So it always has to be in this, but is it the C4, is it a C8? So in terms of this, I'm going to work out, well, what is my mass of this original one? So 4 times 12 for my carbons is 48. My nitrogen is 14, so I'm going to need to add 14. My hydrogen, there are 11 of them, and so that will be 11, which is a mass of 73. So my parent molecule, in this case, is molecular formula is C4NH11, because the highest mass parent ion, or the M+, is equal to 73, and the mass of C4NH11 equals 73. So I've done the molecular formula in terms of here, and I've justified my answer using information from the mass spectrometer, and it was worth 2 marks. So 1 mark would have been for the molecular formula and 1 mark for your justification. So then it asks me to identify the fragment that produces the base peak. Now you need to remember that the base peak is your tallest peak, and it's called that because it's then the basis in terms of it becomes 100%, and everything else in terms of the percentage is based on relative to that. So the percentage of that peak is then relative to that peak. So our base peak is our tallest peak, and it occurred at 30. So then we've got to look at, based on this molecular formula, what could our fragments be? So we know that it's a primary amine because we worked that out from the infrared spectra. So we have an NH2 at the end. Then we have 4 carbons, and we need to distribute 2 less because we've already used, so we need to distribute 9 hydrogens amongst those. So if I had 2 on each of these and 3 on the end, then that would be 9 hydrogens. So then we're looking at, well, what sort of fragments could I actually get from this? So I could have my NH2, which would be 14 plus 2, that would be just 16. I then could have a fragment here, a CH2, NH2, which would be the 16 that I had here, plus another 14. So this would actually be 30. So this fragment here would actually add up to 30 because we have 12 plus 2 is 14, plus 14 is 28, plus 2 is 30. Then I'll need to look at, well, could there be other fragments? So if I just had a CH3, CH2, that would be 2 times 12 is 14, and 5 is 29, so it couldn't be this fragment. And a CH2, CH2 would be 28. So the fragment that it is likely to be is the CH2, NH2. So it's likely to be this fragment because that equals mass of 30. So then we've been asked to draw the structural formula for 2 possible structural isomers of the chemical. So it needs to be consistent with both the mass spec and the IR. Now in this case, we know that it was the CH, so I'm just going to write up here my extended molecular formula. There are 4 carbons and then the NH2. So a structural formula means that we have different arrangements of this. So it means I could move the position of where that is. At the moment it's on carbon 1. It could be on carbon 2. Note, because I've only got 4, it can't be on carbon 3 because that would be the same as carbon 2. So one of my possible structural isomers is as I've already drawn it. So we have CH3. So we're going to draw it, I'll draw it for you as an actual, so you can actually see the structure. So continuing with our hydrogens and then our nitrogen. It could also be on the second one, the second carbon. So again, we'd have our CH3. And it doesn't matter if you'd actually done this as on the second here, or on the second here, which means that I would have a CH3 at the end. So notice that the hydrogen here became a CH. And this is why it sometimes does help to actually draw these out with the individual bonds to help you actually work out which one has 4. So the other thing is, because it's a butane, or a but group with 4 carbons, I could actually take one of these CH2s and move it off to the side as well. So then I need to look at, so these are possible, so I could have a, I'll just write this as a, so that's now a 4 with an NH2 here. So then this would become a CH3 and this stays as a CH. So this is another way that I could actually have a methyl group on here. So we're going to have the 4 carbons and we have our primary amine at the end. The other way, there is one other way that it can be, which is my CH3, carbon in the middle, the CH3 here. This could also be my NH2 with a CH3 here. So these are some of the structural isomers. I then need to look at, these would all be consistent with the IR spectra, but I also need to look at, well, is it going to be consistent with the mass spectra? So to do that, we need to look at, well, what fragments. So if I had a CH2NH2, in terms of it, we know that that's our base 30 which exists. So this one and this one have that. Whereas here, if I look at here, I've got my NH2, it's not got a CH2 attached to it any longer. So it actually has only a CH, which would be a 29 rather than the 30. So, and I can't make that 30 in any other fashion. So this isomer is actually not possible or not consistent with the mass spec. So far I have these two. And if I again look here, again for the same reason, I no longer have the CH2. And if I had a CH3 and a C, that's only going to be 25. And that's the only fragments I can make. So this one again is not suitable. So then I would just need to check. So I have this one here, so we've already done that. So I just need to check, have I got a 1, 2, 3, 4, 5, 6, 7, and 3 carbons. So that would be 36 and 7 is 43. And again, 7 and 3. So both of these have a 43. So if I have a look at my mass spec, and I can actually see 41, 40, 41, 42, 43. I do have a small 43 peak, so that is present. Do have a really, really small 29 peak, which is also present, but it means that because I don't have the 30s possible in either of these, that it's not going to be either of these. The two that I would actually say it could be are these two structural isomers. So you've just got to try and look for, have I got the fragments present in the structural isomers that I do. Okay, so that is that for that question.